Well, in this video, we're going to look at something that isn't in the what you'll learn. It should have been. We're going to look at work and rate problems. How are rational equations important in the operation of a subway system? The Washington, D.C. Metro Rail is one of the safest subway systems in the world, serving a population of more than 3.5 million. It is vital that a rail system of this size maintain a consistent schedule. Rational equations can be used to determine the exact positions of trains at any given time. On Saturdays, Lee helps her father install satellite TV systems. The jobs normally take Lee's father about 2.5 hours, but when Lee helps, the job only takes him 1.5 hours. If Lee were installing a satellite system herself, how long would the job take? Just like we're used to, distance equals rate times time. In this situation, rate times time equals jobs. We could easily solve the equation for R, or rate, and say that rate equals jobs over time, or jobs per hour. In this problem, we know that it takes Lee's father 2.5 hours to do one job. So one job, 2.5 hours. We could simplify that. 1 over 5/2 would be the same as multiplying by the reciprocal, so 2/5. It says that when Lee helps, it takes both of them 1.5 hours to install the whole system together. So they're doing one job together, they're working together, so their time is going to be 1.5 or 3/2 each. And we know the father's rate is 2/5. We do not know, we want to find out Lee's rate. So we can cancel, and we have 3/2 times her rate plus 3/5 equals 1. If we subtract 3/5 from both sides, we're going to get 5/5 minus 3/5 would be 2/5. And multiply by the reciprocal of 3/2 is 2/3. And we get her rate to be 4/15. The question asks how long it would take her to do one job by herself. Now that we know her rate is 4/15, we're trying to find her time, and she's just doing one job. We can multiply both sides by the reciprocal again. And so we get her time to be 15/4. That's awkward. Or we'd be more likely to say 3 3/4 hours. That's one type of rate problem. The next type is famous, the train problem, are called uniform motion problems. A drawing is always helpful. The schedule for the Washington, D.C. Metro Rail is shown at the right. Suppose two red line trains leave their stations at opposite ends at exactly 2 p.m. One train travels between the two stations in 48 minutes, and the other train takes 54 minutes. At what time do the two trains pass each other? We go down the road in miles per hour in this country, so it's not a big stretch to know that rate is distance divided by time. So for the first train, it takes it 48 minutes to cover the 19.4 miles. The second train's a bit slower. It takes 54 minutes to cover the same distance. Now, the two trains are running on different tracks. They're not going to crash, but they will meet somewhere in the middle. And distance equals rate times time. So the first train will travel. It doesn't divide out well at all, so I'm just going to leave it 19.4 divided by 48 times the amount of time it takes. And the second train will travel 19.4 divided by 48 times the same amount of time because they're meeting. So why do we need to be able to find least common multiple? So we can find out when trains meet. I'd like to know what the least common multiple of 48 and 54 is. Not even going down to primes, I can see that they have a common factor of 6. So they both have a 6, I need an 8, and I also need a 9. Okay, 6 already used. So 48 times 9, or 432, is going to be my least common multiple. And now it unravels pretty quickly. When we distribute, we're going to have 174.6t plus 155.2t equals 8,380.8. Combine our like terms, we get 329.8t equals same number. And divide by 329.8. And I get that it'll take them about 25.41 minutes rounding to the nearest hundredth. Rereading the original question, it asked, at what time do the two trains pass each other? Fortunately for us, they left at exactly 2 p.m., so they will cross each other at about 2:25 p.m. Now we have some more just solve problems. Nice, least common multiple is x minus 1. If we multiply both sides by x minus 1, I just get 3 equals x plus 2. Subtract 2 from both sides, and x equals 1. But wouldn't you know, when we go to check, 1 minus 1 is 0. Division by 0 is undefined. So I have to throw out my answer, and this is going to be a no solution problem. So it's really important to do a check step because multiplying each side of an equation by the least common denominator of two rational expressions can yield results that are not solutions to the original equation. Recall that such solutions are called extraneous solutions. Once again, we can multiply both sides by x minus 2 and cancel. Lovely. So I get 4x squared equals 4, or x squared minus 4 equals 0. We can factor that into x plus 2, x minus 2, because it's difference of squares. And so our two solutions are negative 2 and positive 2. Instead of factoring, you could have taken the square root of both sides, and the square root of 4 should be plus or minus 2 because negative 2 times negative 2 is also 4. The factor one is kind of nice because I can see easily when I substitute 2 back in, bad things happen. I get division by 0, it gets thrown out. So the only solution that's going to work is negative 2. The work and rate problems gave us the opportunity to multiply every term of more complicated rational equation by the least common denominator to eliminate fractions. And be warned, watch out for extraneous solutions.